In this video, we're going to talk about section 4.7 that deals with Hopital's rule. And in this section, we're going to be finding limits. So now we're revisiting limits. This time, we're going to be using Hopital's rule to find limits when your expressions are in the form of 0 over 0, and also in the form of 0 times infinity, no, infinity over infinity, I'm sorry, and also 0 times infinity and infinity minus infinity. Okay, those are the forms that we will be looking at. 0 over 0, infinity over infinity, 0 times infinity, and infinity minus infinity. We'll look at those and how to take limits. Okay, so now back in chapter 2, if you recall, we did talk about limits. Okay, now some limits in this case are called indeterminate forms. Okay, and those are the ones that generally can be evaluated or generally cannot be evaluated using those techniques that were presented back in chapter 2. Okay, so here these limits tend to be the more interesting limits that arise in practice. So a powerful result called Hopital's rule enables us to evaluate limits, such limits like these, with relative ease. Okay, so the first way, or the first rule for Hopital's rule, is when you have limits that are in the form of 0 over 0. That means the limit of the numerator goes to 0 and the limit of your denominator goes to 0. So let's say I want to consider a function of the form f of x divided by g of x and assume that the limit as x approaches some value of a of f of x and the limit as x approaches a of g of x is equal to 0. Then that means that the limit as x approaches a of f of x divided by g of x has an indeterminate form of 0 over 0. Okay. So now let's look at this theorem that deals with a case where you have 0 over 0 when you take the limit of the numerator and the denominator. Suppose f and g are differentiable on the open interval I containing a with g prime of x not equal to 0 on I. When x is not equal to a, if the limit as x approaches a of f of x equaling to the limit as x approaches a of g of x at both equals 0, then here's Hopital's rule. The limit as x approaches a of f of x divided by g of x will be equal to the limit as x approaches a of f prime of x divided by g prime of x. In other words, you're going to take the derivative of the numerator and the derivative of the denominator and take that limit if you are able to do so. Now, the provision is that the limit on the right side exists or is plus or minus infinity. The rule applies if x approaches a is replaced by x approaches plus or minus infinity, or x approaches a from the right, or x approaches a from the left. Okay. Now, if you're not familiar with limits, my suggestion is you go back to those videos that I discussed in chapter 2, and also those videos should be on Canvas for you to review. All right, so now let's take a look at this first example. We're going to apply Hopital's rule, which is that theorem that I just presented to you, to evaluate the limit as x approaches -3 of x squared plus 8x plus 15 divided by -12 minus 1x plus x squared. Now, if you were to use direct substitution, and I'm going to do this on the calculator to show you. So if you use a direct substitution by substituting the x in the numerator with -3, you'll have this -3 and then squared plus 8 times -3 plus 15. That numerator will be 0. As for the denominator, if I do -12 minus 1 times x, which is -3, plus negative 3, and I squared, I'm also going to get 0. So here I do have the indeterminate form of 0 over 0. So that means here I'm going to apply L'Hopital's rule by taking the derivative of the numerator and the derivative of the denominator, and then I'm going to evaluate that limit. So here I have a limit as x approaches negative 3. The derivative of x squared plus 8x plus 15, that's going to be 2x plus 8. And then the derivative of the denominator, which is negative 12 minus 1x plus x squared, where the derivative of negative 12 is 0. The derivative of a negative 1x will be negative 1 plus the derivative of x squared, that will be 2x. Okay. Now, if I was to do direct substitution here, I'm not going to get a 0 in the denominator, nor will I get the indeterminate form. So here I can replace each x with negative 3. So this will be 2 times negative 3, and then plus 8, all divided by negative 1 plus 2 times negative 3. Now, if I simplify this, negative 2 times 3 will be negative 6 plus 8 over negative 1. And then 2 times negative 3 will be minus 6. Negative 6 plus 8 will be 2. Negative 1 minus 6 will be negative 7. So this will end up being negative 2/7. So here the limit as x approaches negative 3 of x squared plus 8x plus 15 divided by negative 12 minus 1x plus x squared using L'Hopital's rule would end up being negative 2/7. Okay. All right, here's another example. Example 2 looks like this. Here I'm going to evaluate this limit using L'Hopital's rule. Here I got the limit as x approaches negative 1 of 6x to the 4th plus 8x cubed plus x plus 3 divided by x plus 1. Okay. Now, if I was to replace each x with negative 1, and I'm doing this in the calculator, by the way, to show you that what's going to happen here is you're going to get a 0 in the denominator. I have a 0 for the numerator. Now, negative 1 plus 1 automatically gives me 0. So 0 over 0, that's the indeterminate form. So that means I need to go ahead and apply L'Hopital's rule. So I'm going to bring over the limit as x approaches negative 1. Then take the derivative of 6x to the 4th plus 8x cubed plus x plus 3. Well, the derivative of 6x to the 4th will be 24x cubed plus the derivative of 8x cubed will be 24x squared plus the derivative of x is 1. And of course, the derivative of 3 is 0. Now, my denominator, the derivative of x plus 1 would just simply be 1. And of course, I'm not going to get that indeterminate form of 0 over 0 when I replace the x with negative 1. So this is just going to be the limit as x approaches negative 1 of, well, 24x cubed plus 24x squared divided by plus 1, all divided by 1 is just 24x cubed plus 24x squared plus 1. Now I have a polynomial, which I can go ahead and apply direct substitution. So I can just go ahead and substitute each and every x with negative 1. So this will be 24 times the negative 1, that's cube, plus 24 times x, which is negative 1, that's squared, plus 1. Well, if I cube a negative, that's going to be negative. So negative 1 cubed will be negative 1 times that 24, which is negative 24 plus square the negative 1 will be positive 1 times 24, which is 24 plus 1. And then when I simplify this, of course, negative 24 plus 24, that adds to 0, so that's gone. And I'll be left with just 1 as the final answer. So in this case, the limit as x approaches negative 1 of 6x to the 4th plus 8x cubed plus x plus 3 divided by x plus 1 ends up being 1, applying Hopital's rule. Okay. All right, let's go to the next example here, where we're going to evaluate that limit using Hopital's rule. Here we got the limit as x approaches 0 of e to the 2x minus 1 divided by 3x squared plus 2x. All right, so if I was to do direct substitution here, this will be e to the 0, which is 1. 1 minus 1 is 0. The denominator is going to end up being 0 because each x will be substituted with 0. So I will have the indeterminate form of 0 over 0, which means I need to apply Hopital's rule. So here I'm going to have a limit as x approaches 0, bring that over. Take the derivative of e to the 2x minus 1. Well, for e to the 2x, the derivative of e to the 2x will be e to the 2x. But then I have to multiply that by the derivative of 2x. I have to apply that chain rule. So the derivative of 2x will be 2. And I'm going to put the 2 in front of e to the 2x. And the derivative of minus 1 will be 0. Now for the denominator, I take its derivative. The derivative of 3x squared will be 6x plus the derivative of 2x will be 2. Now I'm not going to get a 0 in the denominator, and I'm not going to get the indeterminate form, so I can apply direct substitution. So here I'm just going to substitute each x with 0. So I got 2 times e to the 2 times 0 divided by 6 times x, which will be 0, plus 2. Well, here, if I do 2 times 0, that's 0, but e to the 0 is automatically going to be 1, and 1 times 2 will be 2. 6 times 0 is 0, plus 2 will be 2. 2 divided by 2 ends up being 1. So the limit as x approaches 0 of e to the 2x minus 1 divided by 3x squared plus 2x will end up being 1 using Hopital's rule. Okay, here's another example. This time, we're going to look at one dealing with trig functions here using Hopital's rule. Here we've got the limit as x approaches 0 of 9 sine of 3x divided by 2x. So if I use a Hopital's, direct substitution, you're going to see that 9 times the sine of 3 times 0 ends up being 0. And the denominator, 2 times 0, will be 0. Excuse me. So in this case here, I will get 0 over 0, which is the indeterminate form. So now I need to apply Hopital's rule by taking the derivative of the numerator and the derivative of the denominator. Well, the limit as x approaches 0, I have to bring that over. Let's see, the constant is a 9, I'll bring that over. The derivative of sine of 3x. Well, if you recall, the derivative of the sine is going to be the cosine and of 3x, but we got to use the chain rule by taking the derivative of 3x, which is 3. All that's divided by the derivative of 2x will be 2. Now, if I simplify this, I'm going to have a limit as x approaches 0. 9 times 3 will be 27. So it'll be 27 times the cosine of 3x. All that's over 2. And again, I'm not going to get the indeterminate form because my denominator is not going to be 0. So here I can apply direct substitution. So that means I have 27 times the cosine of 3 times 0. All that's divided by 2. And 3 times 0 is 0, so this will be 27 times the cosine of 0, all over 2. Now, if you recall, back in section 1.4, when we were dealing with the unit circle and angles, the cosine of 0 is going to be 1. Cosine of 0 is going to be 1. So I got 27 times 1 divided by 2, or just 27 over 2. Okay. Now, I would advise you that if you're not familiar with what cosine of 0 is and what sine of 0 is, or any of your angles, I would recommend that you pull up the unit circle back in section 1.4 that I talked about in one of the previous videos, and check out that unit circle, okay? Because we'll be using that in a few of these examples here, like in example 5 that I'm going to present to you. And here it is. So here we're going to use Hopital's rule to evaluate the limit as u approaches pi over 4 of 3 times the tangent of u minus 3 times the cotangent of u divided by 2u minus pi over 2. Okay. And I will get a 0 over 0, which is the indeterminate form, because at pi over 4, the tangent of pi over 4 is, that's going to be 1, I believe. Yeah. Yeah, tangent of pi over 4 is going to be 1. So here, tangent of, and let me do this here. I need to change the mode to radians, which is what I have here. And then I'm going to do second half key for the pi divided by 4. That will be 1. So 3 times 1 will be 3. Cotangent is the reciprocal of the tangent. And tangent of pi over 4 will be 1. So cotangent of pi over 4 will also be 1. So this will be 3 minus 3, which is 0. The denominator, if I substitute the u with pi over 4, that would be 2 pi over 4, which is pi halves, minus pi halves, which is also 0. So I'm going to get 0 over 0 in as an indeterminate form. So that means I need to apply Hopital's rule. So I'm going to bring up the limit as u approaches pi force. The derivative of the tangent, and I'm going to bring the 3 over, the derivative of the tangent of u, and you have to go back to chapter 3 to find those derivatives of your trigonometric functions. The derivative of the tangent of u is the secant square of u. And then minus 3 times, I need to take the derivative of the cotangent of u. Again, back to the derivatives of your trig functions, the derivative of the cotangent will be negative cosecant square of u. And all of that is divided by the derivative of 2u will just be 2. But pi over 2, that's a constant, and the derivative of a constant is 0. So all you have there is a 2 in the denominator. And we're not going to get a 0 over 0 situation here. Now, let's simplify this a bit. I have the limit as u approaches pi over 4. That's equal to 3 sine secant square of u. Three secant square of u. A minus and that negative will make that a plus 3 cosecant square of u. All that's divided by 2. Now we can use direct substitution here. And when we do direct substitution, you just go ahead and substitute our u with pi over 4. So I have 3 times the secant square of pi force plus 3 times cosecant square of pi force. The whole thing is going to be divided by 2. Now off to the side, I'm going to evaluate secant of pi over 4. Okay. First of all, let's talk about the secant of pi over 4. And if I can figure that out, I'll just square that. All right, secant of pi over 4, I know something about a reciprocal identity for the secant. That's actually 1 over the cosine of pi over 4. Okay, secant is actually 1 over the cosine of pi over 4. Okay, and I know this, that the cosine of pi over 4 will be the square root of 2 over 2. So that means I'm going to have 1 over the square root of 2 all over, well, over 2. Now I need to simplify 1 over the square root of 2 over 2. What I'm going to do here, since I got this 2 in the denominator, I'm going to multiply the numerator and the denominator of that complex fraction by 2. And when I do that, here I'm going to have 1 times 2, which is 2, divided by the square root of 2 over 2 times 2. These 2's divide out, you'll be left with the square root of 2 in the denominator. Okay, now I'm not going to rationalize the denominator, and you're going to see why. Because since the secant of pi over 4 is equal to 2 over the square root of 2, I want secant square of pi over 4. All I have to do there is just take the value of the secant of pi over 4 and square it. So this will be 2 over the square root of 2, and I'm going to square it. So here I'm going to have 2 squared, which is 4, divided by the square root of 2, and I square it. That's going to get rid of that radical, leaving me with a 2. And then 4 divided by 2 will end up being 2. So in this case here, the secant square of pi force ends up being 2. So here's what I'm going to have. I have the 3 in front. Secant square of pi over 4, that's 2. So it'll be 3 times 2 plus 3 times. Now for the cosecant square of pi over 4. The cosecant square of pi over 4. Now I'm going to need to do this on a second sheet of paper, like this. Let's find out what the cosecant of pi over 4 is going to be. Now the cosecant as a reciprocal identity will be 1 over the sine of pi over 4. And the sine of pi over 4, I know what this is. That's going to be 1 over the square root of 2 over 2. Because sine of pi force is the square root of 2 over 2. So I have 1 over the square root of 2 over 2. And then I'm going to do like I did with the secant being 1 over cosine of pi over 4. I'll multiply that numerator and the denominator by 2. So this will be a 2 in the numerator. And of course, the 2's divide out here. I'll be left with the square root of 2. And then to find the cosecant square of pi over 4, I'll take that 2 over the square root of 2 and square it. So that means the numerator will be 4 over the square root of 2 over 2. Well, the square root of 2 and you square it will just be 2. It wipes out the radical. So 4 divided by 2 will be 2. So the cosecant square of pi over 4 would end up being 2. So in this problem, this is what I'm going to have. 3 times the cosecant square of pi over 4, that's also 2. All of this will be divided by 2. All right, so now let's simplify that numerator. 3 times 2 is 6. Plus 3 times 2 again, that's 6. Divided by 2. 6 plus 6 is 12. 12 divided by 2 is 6. So the limit as u approaches pi over 4 of 3 tangent of u minus 3 cotangent of u divided by 2u minus pi over 2 ends up being 6. Okay. So it all goes back to the knowledge of the values for pretty much sine and cosine, and also your derivatives for your 6 trigonometric functions. Okay, so review those. All right, here's another example of something that has 0 over 0. The limit as v approaches 7 of v minus 2 minus the square root of v squared minus 24 divided by v minus 7. And I will get a 0 over 0 in this case here because replacing the x, the v was 7. This is 49 minus 24, which would be 25. 7 minus, and then the square root of 25 will be 5. 7 minus 2 will be 5. 5 minus 5 will be 0. And of course, I get the 0 in the denominator as well. So we'll have to apply Hopital's rule. All right, so let me write the limit as v approaches 7 and take its derivative. The derivative of v is going to be 1. The derivative of a minus 2 will be 0. And then I got the minus in front of that. The derivative of v, the square root of v minus 24. Well, I know this. If I take the derivative with respect to x of the square root of x, that ends up being 1 over 2 square root of x. So I'm going to apply that to this derivative here. This will be 1 over the square root of that v squared minus 24. But I have to apply the chain rule by taking the derivative of v squared minus 24, which will end up being 2v. And I left off the 2 in front of that square root. Okay, square root of x's derivative is 1 over 2 square root of x. So the derivative of the square root of v squared minus 24 has to be 1 over 2 square root of v minus 24. And then times its inside derivative of 2v. Now and also I need to take the derivative of the denominator before I do anything else. The derivative of v minus 7, or the derivative of v is 1. The derivative of the constant is 0. Now I can divide out the 2's here. So I will be left with the limit as v approaches 7. And all of this divided by 1 will be all of this in the numerator. So all I'm going to have here is 1 minus 1 divided by, well, actually, 1 times the v, that's going to be the v in the numerator. So I have 1 minus the v in the numerator divided by v squared minus 24. And now I can apply direct substitution here. So this will be 1 minus v, I replace that with 7, divided by the square root of v again, that's 7. That will be squared minus 24. Simplify this will be 1 minus the 7 in the numerator. 7 squared is 49 minus 24 will be 25. So I have the square root of 25 in the denominator. And the square root of 25 is 5. So I have 1 minus 7/5. And if you want to do this in the calculator, do 1 minus 7/5. 1 minus, and in parentheses, 7 divided by 5. Press the math key, select number 1. And this will give you -2/5. So the limit as v approaches 7 of v minus 2 minus the square root of v squared minus 24, all divided by v minus 7, will end up being -2/5. Okay. All right. Now, Hopital's rule requires evaluating the limit as x approaches a of f prime of x divided by g prime of x. It may happen that this second limit is another indeterminate form to which Hopital's rule may be applied again. So the ones that we've been doing in these examples where we only applied Hopital's rule once, but sometimes you may have to apply it again and again until you do not get an indeterminate form. Okay, so let's look at this one. Here's another indeterminate form for infinity to infinity. So here Hopital's rule applies directly to limits of the form f of x, of the form the limit as x approaches a of f of x divided by g of x, where the limit as x approaches a of f of x plus or minus infinity, and the limit as x approaches a of g of x is also plus or minus infinity. This indeterminate form is denoted as infinity over infinity. And here is that theorem for that one. So if you have to apply Hopital's rule for infinity to infinity divided by infinity, it's going to be this. You're still going to have to take the derivative of the numerator and the derivative of the denominator, and then take that limit. Okay, and that rule still applies for plus or minus infinity, and that's provided that the limit on the right side exists or is plus or minus infinity. It also applies for x approaches plus or minus infinity. Also, x approaches a to the right and x approaches a to the left. Okay, so it's pretty much the same Hopital's rule, but it's just for infinity over infinity. All right, so now let's look at this example. Let's say I want to evaluate this limit. The limit as x approaches infinity of 4x to the fourth minus 3x squared divided by 5x to the fourth plus 5. Now, the numerator, if I look at this, this will go to positive infinity. The denominator will also go to positive infinity. So I do have a situation of infinity divided by infinity. So I need to apply Hopital's rule on this problem. So I'm going to bring over the limit as x approaches infinity. Take the derivative of 4x squared minus 3x squared. 4x to the fourth minus 3x squared. Well, for 4x to the fourth, that derivative is 16x cubed minus the derivative of 3x squared will be 6x. Divided by, for 5x to the fourth plus 5, the derivative of that will be 20x cubed. Okay. Now, in this case here, we still have a situation of infinity over infinity. Okay, because the numerator is going to go to infinity, the denominator also goes to infinity. So we have to apply Hopital's rule again. So now you got the limit as x approaches infinity. Let's take the derivative of 16x cubed. that will be 48x squared minus 6. The denominator will take the derivative of 20x cubed. That's going to be 60x squared. All right, again, I'm going to get infinity over infinity because the numerator is going to go to infinity. The denominator will also go to infinity. So I have infinity over infinity again. That means I need to apply Hopital's rule again. So I'm going to bring down the limit as x approaches infinity of the derivative of 48x squared minus 6 will be 96x divided by the derivative of 60x squared will be 120x. Okay, so I'm still going to bring down the limit as x approaches infinity. Okay, there are two ways you can do this. You can divide out the x and you'll be left with 96 over 120, or use Hopital's rule again by taking the derivative of 96x, which will be 96, over the derivative of 120x will be 120. And that's because I'm going to still have a situation of infinity over infinity. Now, I can take the limit of a constant. If you recall, the limit of any constant is that constant. So I'm going to end up with 96 over 120. But I need to reduce that in its simplest form by dividing the numerator and the denominator by 24. Now, if you didn't know that, you could do this. 96 divided by 120. Press the math key, number 1 for fraction. It'll give you the fraction in its simplest form, which is in this case 4/5. So after all of that, the limit is x approaches infinity of 4x to the 4th minus 3x squared divided by 5x to the 4th plus 5 ends up being 4/5. Okay, let's take a look at another example. So we have something like this. The limit as x approaches infinity of x squared minus ln of 2 over x divided by 8x squared plus 2x. And by looking at this, I do have an infinity over infinity situation because looking at this leading term, x squared, that limit will go to infinity. But 8x squared, that too is going to go to infinity. All right. So now we need to use Hopital's rule. All right, so here's what we got. Bring up the limit as x approaches infinity. Let's take the derivative. Well, actually, before I do anything, I need to write that 2 over x as an expression with a negative exponent. So I'm going to bring over x squared minus ln of, and in parentheses 2, that x to the 1, if I take that out of the denominator, it would become x to the negative 1. All that's divided by 8x squared plus 2x. And then next, we'll go ahead and use Hopital's rule, which is the limit as x approaches infinity. The derivative of x squared will be 2x minus the derivative of the natural log of 2x to the negative 1. That will be 1 over that expression, 2x to the negative 1. However, I need to take the inside derivative using the chain rule. So the derivative of 2x to the negative 1 is going to be this. I bring the negative 1 in front of the 2, multiply, you get negative 2, copy over the x to the 1 less power, negative 2. And all that's going to be divided by the derivative of 8x squared will be 16x. and the derivative of the plus 2x will be plus 2. Okay, now I'll need to clean up this numerator here. So on the next line would be the limit as x approaches infinity of 2x minus. Now, if I take that x to the -1 out of the denominator, that's going to change to a positive x to a positive 1 power. So this will be x in the numerator over 2 times the -2 will be in the numerator, and x to the -2, if I write that using positive exponents, the x goes in the denominator as x to the positive 2. And again, that's over 16x squared plus 16x plus 2, just 16x. All right, now let's simplify this part a bit, because as you're going to see, the 2's divide out. And one of these x's divides out with an x and the x squared, leaving me with an x here. So next we're going to have, I'm going to bring this up a bit, the limit as x approaches infinity of 2x. A minus, a negative makes that a plus. And I will have, in this case, an x in the denominator. So I'm going to have a 1 over x here over 16x plus 2. Okay. All right, now again, I'm going to write that 1 over x as this. The limit, I'm going to bring down the limit as x approaches infinity, 2x plus 1 over x using negative exponents will be x to the -1 divided by 16x plus 2. Notice I'm still going to have a infinity over infinity situation here, because 2x goes to infinity, 16x also goes to infinity. So I need to apply Hopital's rule again. So bring down the limit as x approaches infinity. The derivative of 2x will be 2. The derivative of x to the -1. So if I bring the -1 down, that's going to be minus, copy over the x to the 1 less power, that'll be x to the -2, divided by the derivative of 16x will be 16. And of course, the derivative of 2 will be 0. All right, so what I need to do here is continue this over here somewhere. This will be the limit as x approaches infinity of 2 minus x to the -2. If I write that using positive exponents, will be 1 over x squared divided by 16. So now I no longer have the infinity over infinity situation. All right, so here's what's going to happen. That should be equal sign. This will be equal sign. Notice what's going to happen as I let x approaches infinity. That 1 over x squared, that's going to go to 0. There's a rule back in chapter 2 when we were dealing with limits at infinity. As we let x approach infinity, then 1 over x to whatever that power is will go to 0. So as x approaches infinity for the limit of 1 over x squared goes to 0. So we'll be left with just 2 over 16. And 2 16ths reduces to 1/8. Okay. So the limit as x approaches infinity of x squared minus ln of 2 divided by x squared plus 8x squared plus 2x will end up being 1/8. Okay. All right, let's look at some related indeterminate forms like 0 times infinity and infinity minus infinity. And I believe that would be the last thing I will cover in this video. There are other indeterminate forms, but that are discussed in this section on Hopital's rule, but I'm not going to cover those here. Because each limit is different, it is clear that the form 0 times infinity and infinity minus infinity are indeterminate in the sense that it does not determine the value or even the existence of a limit. Basically, you attempt to convert each of these forms to either 0 over 0 or infinity over infinity so that Hopital's rule can be applied. Like in this example here, example 9. Let's say I want to evaluate the following limit. The limit as x approaches 0 of x times the cotangent of x. Well, if you look at this here, I know for x, if I substitute the x with 0, that's going to be 0 times the limit as x approaches 0 for the cotangent of x. That's going to be going to infinity. So I do have a situation of 0 times infinity. So I need to write this in a way so I will have infinity over infinity or 0 over 0. And that way I can apply Hopital's rule. All right, I know one of the identities here, let me bring up the limit as x approaches 0 of x times, I know the reciprocal identity for the cotangent of x. The cotangent is always going to be 1 over the tangent. So I'm going to write cotangent of x as 1 over tangent of x. And that would mean I will have a limit as x approaches 0 of x over tangent of x. I'm just multiplying it. Now, here's what I have here. I have a 0 in the numerator. The denominator, the tangent of 0 is 0. So I do have 0 over 0. So here I can apply Hopital's rule. So at the limit as x approaches 0, the derivative of x is going to be 1 over the derivative of the tangent of x will be secant square of x. Actually, I can do direct substitution instead of writing this limit over. So here's what I'm going to have. I know I'm going to have a 1 in the numerator over. I could go and do direct substitution of secant square of 0. And if you recall, the secant is always 1 over the cosine. Cosine of 0 is 1. So that means that the secant square of 0 will also be 1. So I have 1 divided by 1, and that's going to end up being 1. Okay. So here you have to know that the secant is going to be 1 over the cosine. Cosine of 0 is 1, so secant of 0 must be 1. And secant square, well, secant square has to be 1 as well. So the limit as x approaches 0 of x times the cotangent of x will be 1. Okay, here's another example. Or I should say next to the last example. So we have this limit that we want to evaluate. The limit as x approaches 0 of the cosecant of 2x times the sine of 8x. Well, let's think of this. The cosecant of 2x is like 1 over the sine of 2x. That's going to go to infinity. Sine of 8x as we let x approach 0, that's going to be 0. So I do have 0 times infinity, just like I did in the last example. So we need to write this in a way that we can have either infinity over infinity or 0 over 0. That way we can apply L'Hopital's rule. So the limit as x approaches 0, let's see, the cosecant of 2x is going to be 1 over the sine of 2x. It's one of those trig identities, reciprocal identities in trig. And then that's multiplied by the sine of 8x. So if I simplify this a bit, you'll see that the limit as x approaches 0 of the numerator will be sine of 8x. The denominator will be sine of 2x. Sine of 0 is 0. So that means I do have a 0 over 0 situation here. That would mean I need to apply L'Hopital's rule. And applying L'Hopital's rule, I will take the derivative of the numerator and the denominator. So the limit as x approaches 0 of this. The sine of 8x, if I take the derivative of that, that's going to be, of course, cosine of 8x. But I need to take the inside derivative using the chain rule. The derivative of 8x will be 8. And I'm putting the 8 in front of the cosine of 8x. Same thing here for the derivative of sine of 2x. That's going to be cosine 2x, but I got to take its inside derivative. The derivative of 2x would be 2. And now I can apply direct substitution here because I know something about the cosine of 0. That's going to be 1. So if I do direct substitution, this will be 8 times the cosine of 8 times 0 divided by 2 times the cosine of 2 times 0. 8 times 0 is 0. Cosine of 0 is going to be 1. The denominator will be 2 times. 2 times 0 is 0. The cosine of 0, again, that's going to be 1. So this will be 8 divided by 2, which ends up being 4. So the limit as x approaches 0 of cosecant of 2x times sine of 8x will be 4. Okay. And finally, example 11 on your handout. Here we got the limit as theta approaches pi over 2 from the left of 11 tangent theta minus 11 secant theta. All right. In this case here, tangent theta at pi over 2 from the left is going to go to infinity. Secant theta, as we let theta approach pi over 2 from the left, that's also going to go to infinity as well. So I will have a situation of infinity minus infinity. So L'Hopital's rule will need to be used here. And I need to write this in the form of something like infinity over infinity or 0 over 0 for me to use L'Hopital's rule. So here's what I'm going to do here. I have the limit as theta approaches pi halves from the left of tangent of theta. I'm going to write that as sine theta over cosine theta. That's one of our reciprocal identities here. So I have 11 times sine theta divided by cosine theta minus 11 times. Now, secant of theta is a reciprocal identity. That's going to be one of the cosine of theta. Okay, so let me bring down the limit as theta approaches pi halves from the left of, if I multiply 11 times sine theta over the cosine of theta, I'm going to have 11 sine of theta divided by the cosine of theta minus 11 times 1 over the cosine of theta. That's just going to be 11 over the cosine of theta. And notice when I combine these two, the denominators are exactly the same. So I can write all of that numerator over the single denominator. So I'll bring down the limit as theta approaches pi over 2 from the left of this 11 sine theta minus 11. That whole thing is divided by the cosine of theta. Now I know sine of pi over 2 will be 1 times 11, which is 11. 11 minus itself will be 0. Cosine of pi over 2 is 0. So I do have a situation of 0 over 0. So I can apply Hopital's rule by taking the derivative of the numerator and the derivative of the denominator. All right, so limit as theta approaches pi over 2 from the left. The derivative of the sine is the cosine. So that's going to be 11 cosine theta. The derivative of 11, that's going to be 0. The derivative of the cosine of theta is going to be negative sine of theta. Okay, that's one of our derivatives of our trig functions, to be familiar with that. Now I can go ahead and do direct substitution by substituting each theta with just pi over 2. So in this case here, this will be 11 times the cosine of pi over 2 divided by negative sine of pi over 2. Cosine of pi over 2 will be 0, so this will be 11 times 0 over the sine of pi over 2 is 1, but I do have the negative in front of that, so that'll be negative 1. And then 11 times 0 is 0, divided by negative 1 ends up being 0. So the limit as x approaches pi over 2 from the left of 11 tangent theta minus 11 secant of theta ends up being 0. Okay. All right. So that does conclude this video on section 4.7, dealing with Hopital's rule. All right. Feel free to contact me if you have any questions about the homework in my math lab, or if you have any questions about any of the problems that I presented in this video.